Today, our webinar, we're going to be talking about tunnel lining systems manufactured by Agru-America with a special focus of tunnel waterproofing systems. And as we go along, you'll see that there are a few other products we make that can be used in tunneling, but this is specifically directed toward tunnel lining systems for waterproofing for highway tunnels, for light rail tunnels, similar tunnels for transportation and such. So with that, no further ado, we'll talk about that. Here's a little bit of our table of contents of what we're going to talk about today. First, we'll have a brief introduction to Agru. We're going to talk a little bit, just briefly, about our XXL pipe, our large diameter piping system. We're going to talk about our tunnel lining and concrete protective liners as used in tunnels. And then we're going to talk about the Agruflex system and how we set that up. Product range and accessories, welding technologies, and finally some reference projects that we've done. So just to tell you a little bit about Agru-America, Agru-America is this year celebrating our 70th year in business. We were founded in Austria in 1948. Agru-America itself has been in business since 1988 here in the United States, so we are celebrating our 30th year. As you see on the screen, a little progression of the products and the that were brought online along. Also, some of the facilities that we brought online over time. Agru is a family-owned business. Most of the products that we make are almost all thermoplastic oriented. We have about 20,000 different products that we manufacture roughly. Various sizes of pipes, different diameters, fittings of various natures, different SDRs on piping systems, thicknesses of liner systems. Just a few of our product offerings right here are what we call product groupings, pipes and fittings. This can be anywhere from large diameter pipes, which we'll talk about, down to tubing systems and ultra pure piping systems for pharmaceuticals and semiconductor industries and such. Semi-finished products. These include sheet stock and round bar stock that might be used to fabricate other products. Concrete protective liners, concrete protection. We're going to talk a little about that today. These are thermoplastic systems that are used to line concrete structures for corrosion and waterproofing. And finally, lining systems, which is going to take up the bulk of what we're speaking about today. These are geosynthetic systems which are used for barrier layers or other layers for drainage or cushioning and such. They include geotextiles, geomembranes, and geocomposite drainage nets. The geomembranes can be used not only in tunnels, but we also use a lot of those in landfill applications, wastewater lagoons, other industries such as water storage and such. So give you a little bit out of there, what all we make there. And here's some of our locations for manufacturing. We have 2 plants in Austria, which is where our worldwide headquarters is. We have a partnership with Frank in Germany, TWS in Poland. In the United States, we have China, which opened, I think, in 2010. And then we have the locations in the United States, which include Georgetown, South Carolina, our U.S. headquarters, Andrews, South Carolina, Fernley, Nevada, and the newest facility is the Charleston Pipe Plant. So here's a little bit about our Charleston Pipe facility. We're making what we call the XXL pipe, or the large diameter pipe. When we say large diameter pipe, we're making the world's largest smooth wall pressure rated polyethylene pipe, up to 3,500 millimeters in diameter. We're able to extrude these pipes in lengths up to 2,000 feet in length and float them out into the harbor, where we can then pull them behind a barge to wherever in the world they need to go. We're not going to talk a whole lot about pipes today, but as they relate to tunnels, we could see these being used as manhole entries to tunnels, access tunnels, intake outfalls to tunnels, and also possibly for slip lining of tunnels, for the smaller diameter tunnels. This is the supply range that we have for our large diameter pipe. As you can see, we go up to 3,500 millimeters, and the SDR range depends on the diameter. I think our maximum wall thickness is about 150 millimeters. So moving on beyond pipes, there are two basic types of lining systems that Agro uses for tunnel lining systems. The first of those that we're going to speak about just briefly is our Sure Grip concrete protective liner. We also have a different design of that called Ultra Grip, which is primarily used in tunnels. This is designed to be the lining on the inner surface of the tunnel. So it's going to protect the tunnel against the corrosive nature of the media that's contained or transmitted within the tunnel. So most often we're going to see this in a sewage tunnel. We make it from HDPE as well as several other resins, but HDPE is the most common and what we've seen in tunnel systems. The second system we're going to talk about, and we're going to spend a little more time today, is our Agruflex tunnel waterproofing system. And this is a smooth geomembrane system that is applied in a tunnel or a cavern or open cut tunnel, cut and cover tunnel. And what we're protecting against there primarily is the seepage of groundwater and any contaminants in that groundwater which may corrode or cause problems with the tunnel infrastructure. Agri uses a VLDPE system primarily for this, a very low polyethylene. And like I said, it's most commonly used in transportation type tunnels, such as light rail, and highway tunnels. First off, we're showing a picture here of tunnel lining with the Sure Grip concrete protective liner. As we said, primarily used for the protection of corrosive media. Most instances is municipal wastewater where there's hydrogen sulfide, and we're lining the inner surface of the tunnel. Here we have a quick little video to give you a little better explanation of that. When we have wastewater in an anaerobic condition, and particularly if the material is in an area that is turbulent, we can generate hydrogen sulfide gas. When that gas reaches the upper structure of the tunnel, it is converted by microbes to uric acid and can cause corrosion of the upper reaches of the tunnel. As you can see, our concrete protective liner, our Sure Grip or Ultra Grip liner, is a flat die calendar extruded material which has anchors that are integrally cast in with the sheet as it is extruded. So we can make this in sheets or rolls up to 5 meters in width. We have these anchor studs. There's about 420 of those per square meter. Very high shear resistance due to the fact that the anchors are cast integrally with the liner itself. The placement of the studs is diagonally. For this reason, we see a much better attachment. And we have a different stud types for different pull-out resistance. We've been working with this for 25 or I think 30 years now, actually. If we look at the different anchor types that we have, we want to focus to the far right on our Ultra Grip liner. This anchor is developed as our highest back pressure material. So what we did with it from the original Sure Grip is that we raised the bridge between the two anchors. In the other direction, we flared the edges of the Ys out slightly so that we have attachment in both directions. And this is where we get our highest pull-out resistance. As you can see here in this chart, if we're using the Ultra Grip liner with a sheet thickness of 4 millimeters, we can sustain a back pressure of 1.75 bars in an undrained condition. Now, if we're able to drain the liquid and relieve that back pressure, then we can go with a thinner material and get by with that. But this is for an undrained condition with a sustained back pressure. Here you see the Sure Grip concrete protective liner, or actually the Ultra Grip concrete protective liner, cast in a tunnel. And this is what we call a double shell lining. In this case, you can see on the outside of the tunnel here in the green where my cursor is, that we have the precast concrete segments that are placed as the TBM passes through the tunnel. Between that and on the center, we see the liner system here, which is this yellowish material. And in between that is the inner concrete shell that was cast. So the TBM comes through, it places the precast segments, and then the liner is cast with a subsequent pass by a mobile formwork, hydraulic formwork, which enters the tunnel. We transfer the liner onto that to formwork, and we cast a grout or concrete shell into which that liner is cast. In this case, you can see that we're lining about 320 or 330 degrees of the tunnel. The invert of the tunnel is left unlined, and that is to relieve the back pressure. And remember, we're only concerned about the upper reaches of the structure below the flow line as being affected by hydrogen sulfide gas. In addition to lining as a double segment or double shell system, we can also do a single shell liner. And one of those systems is the Herring Connect combi segments. In this case, what we're doing is we're casting the concrete protective liner directly into the concrete segments when they're cast. So when the TBM comes through and places the segments are already pre-lined. In this case, with the combi segments, there's a turn back, so there's no requirement for welding of each of the segments. In other situations, we may not use the combi segment, just sure grip cast directly into the face. And in that instance, we would need to weld all of the segments together. Here you can see one of the prefabricated combi segment panels and the reinforcement to be placed in the segment. Here's the panel into the formworks and a final cast completed combi segment panel. Some of our references for concrete protective liner in tunnels are the DTSS project in Singapore. That has been in operation since 2005. A year or two ago, we completed the STEP tunnel in Abu Dhabi. Currently ongoing is the Idris Tunnel project. This is a single pass system where we're casting directly into the segments. As of just recently, I understand that we had cast 85,000 segments so far and are continuing. In 2000, we completed operation for cable tunnels in Japan, also a direct cast, and just completed some line sections of the West Trunk sewer in Mississauga, Ontario, Canada. So that gives you a kind of a brief overview without a lot of detail on our concrete protective liner systems for tunnels. Moving on, we're going to go into a little more detail on our Agruflex waterproofing system. So let's talk about what the purpose of the Agruflex system is. First off, we're protecting against seepage water into the tunnel. In a tunnel system, you may have electronics, electrical systems for rails, or highway lights and such, and we want to make sure that we're protected those systems against water intrusion. In addition, we may have special or potentially harmful constituents in the groundwater which may corrode or affect the concrete. So we want to make sure that we protect the concrete and the tunnel structure itself as well. Anytime we design a tunnel, we're looking at typically at a 100+ year life expectancy. So anything that's put in there has to be very long life, watertight, easy to repair, and flexible because it has to conform to the shape of that tunnel. It also has to be easily welded and have good mechanical and chemical resistance. And as we said before, a longevity and a durable product. So in this case, what Agri proposes and what Agri uses and recommends and has been used in extensively is a VLDPE Agruflex tunnel liner. This tunnel liner can vary in thickness between 1.2 millimeters up to 4.2 millimeters. And is available in widths from 2 meters up to 4 meters. We can also do a geotextile backing on this, and we'll explain a little more where we might use that. It can be used in our Easy Fix attachment system, but can also be used to minimize the amount of separate cushioning geotextiles that are used independently. You can see on here that the elongation at break of a VLDPE liner is over 700%, and the E modulus is 700 megapascals. A lot of polyethylene and in tunnel liners is used, but also we'll see some PVC tunnel liners. I want to kind of compare those two products and explain what some of the differences are. And one of the primary differences with the PVC liner from an HDPE liner is that there are a lot of plasticizers that are in that PVC liner. So with a PVC pipe, it's a very rigid product. In order to make that PVC flexible, like you might see in a PVC liner, is why we have the addition of these plasticizers. And they can be to the range of 25% of the material is actually plasticizers. When we're dealing with a polyolefin or a polyethylene specifically, it's comprised of molecule chains of hydrogen and carbon. These molecular chains are very simple, and there's very few additives that are added into the polyethylene. We may put some coloring in there for the white layer and some carbon black in there for stability from UV degradation. And in addition, we may put a very, very small quantity of antioxidants in there for stability. But otherwise, the vast, vast majority of the material itself is polyethylene, and there's nothing that can change within that. In the case of a PVC, the plasticizers that are added to that can potentially migrate out of the PVC over time and cause the material to become brittle. Another advantage of VLDPE over PVC is the density of the material. As you can see, VLDPE has a density of 0.9 grams per cubic centimeters. That's a specific gravity. PVC is 1.3. So much heavier material. So if you're in a tunnel and you're handling this material, it's going to be much more laborious to carry this, to hold it up into place while you're welding it. Here we'll look at some of the basic tunnel elements that we see. Typically in a new Austrian tunneling method, a NATM, or a sequential excavation method tunnel, as you see here, the tunnel will be bored. Shotcrete will be then applied to the walls. A geotextile is used to cushion the geomembrane, and it is placed into the tunnel walls and held in place by discs, which are then used for attachment for the geomembrane in this case. And then inside of that geomembrane, these discs that we see for fixation are temporarily holding the geomembrane in place until such time that this inner concrete shell can be cast. Here's an example of a tunnel sealing system with a full 360-degree cast. If you see the diagram on the far right, you can see that the water table is completely above the tunnel, so the tunnel is completely below the groundwater level, and that there's complete pressure around the tunnel from hydraulic back pressure. In this case, we would probably definitely go for 360-degree lining for that reason. And we would also recommend typically a 3mm liner. The second one is what we would call an umbrella seal. As you can see here, the water table is actually below the tunnel liner, below the tunnel itself. So the water intrusion that we will be seeing will be seepage water and water that's above the water table in the vadose zone that is flowing down towards the tunnel and could potentially leak into it on its way to the groundwater level. With this, we may only allow lining of an umbrella, only of the arch. We may see drainage pipes, or will most likely be required to drain the water as it comes from around the arch. We'll use slotted or perforated drainage pipes to drain this material out. In the event of an umbrella seal, we're not requiring such a thick liner, so typically we may see just a 2mm membrane in that case. We see here the lining of the invert. In the case of a 360-degree lining, we have to do this in 2 stages. First, once the tunnel is bored, we'll come through, line the invert. Subsequently, after lining the invert, then we can cast the floor, creating a ledge for the arch of the tunnel to be poured and cast on. Then secondary, as you see in this picture with the floor already cast in concrete, we'll line the arch or the upper reaches of the tunnel and then ultimately cast that concrete structure. So having talked about the liner, we move on to attachments and how we affix the tunnel liner to the invert and to the tunnel walls itself. As I mentioned earlier, there's typically a cushioning geotextile in place to protect the geomembrane and potentially facilitate drainage in the event of an umbrella tunnel. With that situation, what we would have is we would have discs which are hydraulically or pneumatically shot into the walls of the tunnel. They hold the geotextile in place, and they also act as a point where we can secure the liner to the tunnel face. So these discs, depending on where we are within the tunnel, what position around the tunnel, we may have a higher or lower density of these discs. In the invert, you may only need one per meter or two, or one for every 2 meters. You're just basically keeping the liner from sliding around. On vertical walls where you're beginning to hold the liner in place, you may use 1 or 2 discs per square meter. And where on the top of the arch, we may see as many as 2 to 3 discs per square meter. In this slide, we show 3 different methods for discs, or 3 different discs or methods for fixing these using discs. The traditional system is just a simple plastic disc. This disc is shot into the wall, and then the liner is placed on it. You have to actually reach behind the liner with a Leister, a heat Leister or hot air gun to tack weld the liner onto the disc. Because of this, the typical human arm and the reach with a heat Leister is only about 1 meter. So for that reason, the maximum width that we can make a liner is 2 meters, limited by the ability of someone to reach behind that and weld it. If we can make a wider liner, then we can minimize the number of seams, minimize the number of welds, and basically minimize the potential for poor welds as well, or minimize the potential for leakage. Any case we have a lining system, wherever possible, we want to minimize welding, maximize the manufactured portions of the system. As we move on, looking over to some of the more innovative systems we have, first we have the Easy Fix system. When we make a liner with a fabric backing, our Easy Fix system, the geotextile on the backside is a non-woven geotextile, and this is a looped fabric on there, like a felt. So with the Easy Fix system, we're able to apply a hook and loop type system, like Velcro. So the tabs, rather than use just a plain plastic disc, are a Velcro tab with the hook portion of the Velcro, and the fabric back that is on the geomembrane creates the loop portion, and it can affix just like a Velcro. Finally, the last system we'll talk about is induction welding. This is a very similar disc to the traditional disc. However, there's a wire mesh that is embedded into the face of that disc. When the liner is placed on the top of this, we can actually use an induction welding machine with the paddle that can weld through the geomembrane by activating an alternating magnetic field. So here's the Agruflex VLDPE liner. This is the traditional method. You see the disc being placed, and you can see the worker here on the right with the Leister reaching behind and tack welding the liner onto the disc. In this picture, we see the Easy Fix tabs. These are the Velcro tabs. You can see a detail of those. It's holding the geotextile in place, and the liner is simply pressed into the place on that with the 2 materials bonding in a Velcro-like fashion. And finally, this is an induction welder device. This is a device that, as we mentioned, is used with the induction disc. The processor is on the right, on the left, and on the right is the paddle, which is used to seal it. So the paddle is placed on the geomembrane with the disc behind the geomembrane. The green button on the paddle is pushed. After about 5 seconds, the material will be welded, and another 5 or so seconds of continued pressure. You can remove the paddle, and the material is welded on there. This is a process we're using currently in some tunnels in LA for LA Metro, and it's been proven very successful, and it's helped us to minimize a lot of the seams by allowing us to use very large fabricated panels or manufactured panels. The next accessory we want to talk about is water stop profiles. And the purpose of a water stop profile is to create compartments or segments between the casting joints of the concrete. What this will do is this will allow us in the future to go back in if there is a leak in a compartmentalized area and we have or experienced some problems. Any leaks will be contained within that area. In addition, it will allow us to go in and repair the area that needs repairing in that compartmentalized portion without having to pour grout that may be being injected throughout the entire tunnel. So it creates casting areas or casting segments to minimize the amount of repairs that we have to do in the event that they are required. Here you see a couple of examples of our VLDPE water stops being used. You can see where they create a T that's at the intersection or the corner of a compartmentalization. A little more detail on the water stops. As you can see here, this is what we call a 500/6, a SAA 500/6 water bar. It's 500 millimeters wide. It has 6 primary bars that are used, and as you can see, the casting joint will be in the center of the water stop profile. You see that there are some small little bars that are adjacent to the larger primary bars. These are where we can actually snap the injection tubes into place. So for grout injection, we don't have to have a separate clip. We're able to snap them right into place on the water bar. These are just a few of examples of the stock water bar systems that we have to offer. Primarily, I think the second and third are what we most often see. These are 500 millimeters wide with 6 water stop bars. This is an injection plate. This is used also for grout injection. It's placed on the geomembrane in each of the compartmentalized areas and is tack welded to the geomembrane. The grout hose is then attached to it in the event that we need to grout that area in the future. So some of the welding technology that we use with our VLDPE liners. First off, the hot wedge welding. This is a dual track welding, so it creates 2 welds with an air pocket in between. This is used for the vast majority of the welds. However, in the event that we have repairs to make or detail work or 2 butt welds have to be joined together, then we'll use extrusion welding with the VLDPE extrusion weld rod. Some of the welding machines that we see here on the far right is a wedge welder. This is what we said will make primarily the double fusion welds. We'll make the majority of welds within the tunnel. The second one from the left is a extrusion welder. It has 2 components, a heat leister, which heats up the sheet, as well as a secondary component, which is an extrusion gun, which extrudes a bead of material onto the joint, sealing it and creating one homogeneous material. The third from the left is a heat leister. This can be used for small minor repairs with the weld rod or simply for tack welding materials together. And last, on the far right, is a triac material liner system or welding system. And this is what we'll use for joining the water bar or the water stop profiles to the Agruflex. Here we see one of what we said the double wedge welds. With this seam, there are 2 welds and an air pocket in between. With this, we can pressurize that weld, and we can monitor that pressure and look for a pressure loss to make sure that the weld is competent and there are no leaks in it. In the event that we don't have a double wedge weld, where we have extrusion seams or other detail areas, then we can vacuum box the test. So we use a vacuum test with a similar box like this. There are vacuum boxes that are made for angles, some that may have curvatures to them. With this, we create a vacuum. We soap up the water, the liner within, and look for bubbles that will occur in the event that there's a leak in the liner. So with that, we'll move on to a few of our reference projects that we have throughout the world. One of these you can see that jumps right out is the Palm Island in Dubai. In this case, we did a cut and cover tunnel from the outer reaches of the Palm to the perimeter island around the Palm. Some of the other projects you see here are different stages or phases of lining in tunnels around the world. First project we'll speak about is the Niagara Tunnel project. This was completed probably 3-4 years ago. It is a hydro tunnel. So it's carrying water from above the Niagara Falls down to the Sir Adam Beck Generating Station, which is located downstream of the Niagara Falls. It was a very large diameter tunnel, 14.6 meters, and about 10.2 kilometers in length. About 22,000 square meters of this was a 3mm electric conductive VLDPE, and $180,000 was just a typical standard Agruflex VLDPE lining system that was 3mm. To explain what we mean when we talk about an electric conductive system, the tunnel was originally designed to have a double lining system in a few geologically sensitive areas. Our partner Strabag and Agru got together, and we developed a system where we could detect leaks within the tunnel liner without having to use a double liner system. And we proposed this system, it was accepted, and this is what we used. A lot of the conductive liners you see may have a single electric conductive layer. In the case of the Niagara Tunnel project, we had 2 conductive layers, which allowed us to triangulate between those and use a heat sensor to determine if we had potential damage or leaks in the system. With that, we put an electric conductive layer at the interface of the signal layer between the white and the black, and we also used an electric conductive geotextile. These comprise the dual electric conductive layers. Just a few diagrams of this. This also was done with our Easy Fix system. We saw the geotextile backing on there, which in this case was electric conductive. We used the Velcro tabs in the top right picture. You can see a assisted gantry system, which helped us to deploy the geomembrane up against the Velcro tabs and affix it to the walls. This next project is part of the light rail or subway expansions at the city of Los Angeles Metro. These pictures are from the Crenshaw portion of that, where our materials were extensively used. We are also beginning work on the WSE1 tunnel, the west side, or the Purple Line 1 extension. I believe that Chris 4 is online, and Chris is actually our installer with EC Applications for this project. So I'll take the liberty of talking a little bit about this. In the case of this, we used a high-density polyethylene liner. This was rather than our typical very low-density polyethylene liner. The reason for that is the concern that the owner had over methane. In general, the city of LA has a lot of requirements for gas proofing of its structures. In this case, they call it a hydrocarbon-resistant membrane, and a polyethylene membrane that was high density could easily meet this requirement. Because of that, we were able to use 7-meter wide rolls of material. This helped to minimize the amount of field seams and welds that we used within the tunnel. Also, in the case of West Side 1 and Crenshaw, we only lined the stations and the cross passages, and also some cut and cover applications there. So in this picture here, you see one of the tunnel stations and the 2 twin tunnels leaving the station. In this picture, you see some cut and cover applications. One of these was located at the very foot of the runway at LAX. You can see here that the train is going to be down into a trough. That trough was lined and ultimately will be capped over here. In this picture, you can see the compartmentalization of the water bars, the water stop profiles. And you can see the black-white HDPE geomembrane that was used. Going back, I mentioned this just briefly. This is the cut and cover tunnel at the Palm Island in Dubai. If you look on the top left picture, you can see the concrete structure creating the cut and cover tunnel with the water bar, the water stop profiles already embedded into that, and the geomembrane being attached to that water stop profile and up over the upper portion. The next representative project is the Korombaum Tunnel. This is a tunnel in Austria, and it's a high-speed rail tunnel. Several sections of this pretty extensive tunnel that we've been working on. Did about 132,000 square meters of VLDPE with a thickness of 2.1 millimeters and about 12,000 meters of water stop profile. And this is in the first section. A few pictures there from the tunnel project. The next one is the Blessberg Tunnel. This is the north and south portions of the Blessberg Tunnel. This is located in Germany between Berlin and Nuremberg. It is also a rail tunnel. In this case, we had about 8.3 kilometers, 410,000 square meters of 2 millimeter VLDPE, and about 64,000 square meters, linear meters of water stop profile. And here are some pictures of that tunnel. As you can see, in addition to the typical arch tunnel, we had some shafts that we had to construct as well. Various stages of the lining shown there. The next project is the Schwäbisch Gmünd tunnel. This is a road project. It is located near Stuttgart, Germany. Quite a few tunnel projects going on there. Some of them are rail tunnels. This is a smaller, or I say relatively small compared to the rail tunnels. It's a relatively small highway tunnel there. I think this is just east of Stuttgart. So it's a road tunnel with about 140,000 square meters of VLDPE. In the 3.2 millimeters and 35,000 square meters of 3 millimeter VLDPE. Once again, some more pictures. All of these pictures, as you can see, are of the invert of the tunnel as it is being lined and ultimately cast in the bottom right picture. Feel free to contact me directly if there's anything I can help you with or anything Agri can help you with. We'll make sure to get you the answers you need. Thanks again, and appreciate your joining us today.